A recent study shows that beyond the observable universe, there may be a super-level gravitational source undercurrent if he is confirmed. Today's cosmology is about to collapse. In ancient times, tribes of humans would sit around flickering fireflies, curious about what might lurk in the dark. To this day, this curiosity has not subsided. Our fireflies are getting bigger. Our vision has expanded globally. And beyond that, with the help of people like James Webb, tools like telescopes, our eyes can touch the boundaries of the observable universe. However, there is always a boundary. There is deep darkness. We can only fill it with our imagination. Unknown beyond the universe, the edge of the observable universe. It's an impenetrable barrier. It's the ones in space that are far away from us, so fast, so that there is nothing, including light, to be able to approach us from beyond that line. Therefore, nothing beyond that can be produced with us. Causal link. So it's different from the darkness of the past. The other side of this particular edge, no matter what is hidden, seems destined to remain a mystery forever, because he can never reach us. We can't reach him. Or so we thought. But in 2008, scientists analyzed hundreds of galaxy clusters, and they're going beyond science. The speed of the release is moving towards a certain part of that edge, as if some kind of force was pulling them, or once led them. Its influence spans billions of light years. Something huge, lurking beyond the final darkness. This cosmic flow of galaxy clusters. It's called the undercurrent. What do we know about him? What caused him? And his understanding of the universe. What is the controversial impact of learning? Let's delve into the mysteries of the undercurrent together. And what he told us about the universe, the subversive impact of origin theory. Undercurrents are a controversial issue. So let's start with what we know for sure. In 2001, NASA launched the Wilkinson microwave anisotropy detector. The goal is to map the cosmic microwave background radiation, the faint echo of the Big Bang itself. He silently radiates through all space to help us better understand the characteristics of the universe. This map was completed in 2010, although he released the data in batches before, and it had a huge impact on cosmology, because he helped scientists answer, how flat is the universe, or how much of the universe is made up of matter, compared to dark matter or dark energy. Alexander Kashlinsky is one of the scientists who is eager to get this data. He leads NASA, a research team at Dade Space Flight Center. Kashlinsky was eager to try the cosmic background radiation map compare with the motion of galaxy clusters. Let's see if there are any interesting patterns. It's a tall order to solve this problem. Kashlinsky and his team used a technique called kinematics, Sunyaev, techniques of the Zeldovich effect. It's a very small effect. This technology basically exploits the cosmic background radiation passing through high-energy galaxy clusters. The fact that he gets a little bit of energy, no matter how hot galaxy clusters are. Therefore, it heats up the cooler cosmic radiation, or our galaxy clusters moving fast. So there's a lot of kinetic energy that can be transferred. Anyway, radiation will get a little boost. You can use this information to infer the existence or motion of galaxy clusters. The problem is that the improvement is very small. so that multiple galaxy clusters are required and some statistics to notice him. Researchers need a detailed enough, fine cosmic microwave background radiation pattern than the 1,000 known galaxy clusters can be. Compare. Trying to find movement. To their surprise, they discovered a pattern. Compared to the cosmic microwave background radiation, the massive overall flow of galaxy clusters extend from us light years 250 million universe. Galaxy clusters are traveling at 600-1,000 kilometers per second towards Centauri and Hydra. The mystery is, there's nothing there to explain this movement. Unless there are some huge gravitationists, these galaxies must be pulled towards them, but he's out of our sight. And that led to a suggestion, a particularly large source of mass likely to exist on the edge of our universe, or out of the way, out of our sight. So this was a very controversial idea. But first, beyond the edge of the universe, is it really possible to have a gravitational effect on us? And you might think that the answer is no. As I said at the beginning of the video, now, nothing that exists there can be caused by fruit way affects us. We can't affect anything there either. When empty, it's expanding between 2 points faster than light. Speed time. This is what happens. You lose your ability to interact, even through gravity. But if you were in a period of the Big Bang, and before the expansion of the universe, there is a loophole. For those who are not familiar with the concept, scientists in the 1970s, a strange phenomenon was discovered when we look at large areas of the universe. No matter how many times you magnify, they all look very flat. And at temperature, very similar to the mass distribution. Even before the Big Bang, never touched each other. For example, the left and right edges of our universe, very similar to each other, even if they have no reason to be so, because they never met. This idea is called the world's problem. American physicist Alan Guth realized that if everything in the universe began interacting with each other is like being fully shaken in water, same mix of blue and red dyes, then the problems caused by this puzzle are eliminated, lost, but if so, to make everything in the universe explode, blast to the current position, just need somewhere outside the Big Bang itself. There is a real, positive, fast spatial expansion period, although not sure yet. But physicists put this super. The expansion is located after the start of the Big Bang. Duration is only 0.000000001 seconds, 10 minus 33 seconds. It's not that long. But during that time, he will expand to the 26th power. That's so crazy. This incredibly rapid expansion, similar to from bacteria expand to the size of the Milky Way. All of this, all done in the 100,000th of a trillion seconds. Cosmic expansion events as a Big Bang model. The advantage of type is that he could explain why in the early universe, everything has a chance to mix together, even the parts that don't touch each other now. There are even some very respected theories about how it happened to him. Terms such as scalar fields and false vacuum states are involved, but this theory, the physics involved, is rather complex. This is not the focus of this video. The short answer is, if in the wider reaches of our observable universe, in the vast universe, there is a particularly dense section, then the observability of a particular part of us, the universe, will be affected by its gravity, lean towards him. Then cosmic expansion could happen. transferring the powerful mass from our observable. Zoom out in the universe so that we are no longer affected by his gravitational pull, but because of things in motion, tend to stay active. Galaxy clusters given an initial pull. Now it's just simply going in the same direction, drifting with cosmic currents. As you can see, there are two main reasons for the controversy here. First of all, the undercurrent needs a very large mass, exists outside our universe, to be widely accepted. There must be more stars, more dense than our models currently predict, more concentrated, and this is in line with the idea that the universe is expanding. Uniformity goes against it. The universe as we see it is uniform, or roughly uniform. This means that no matter where you look, the mass is distributed fairly evenly. It's also isotropic. This means that if you take everything that moves in all the galaxies, speed adds up. They cancel each other out. Undercurrents upend the whole idea. He showed that just beyond the visible horizon, things are suddenly not so uniform anymore. That dense mass is still there. We just can't see him. So this is a somewhat outrageous idea. It's also an idea that raises a lot of questions. If the universe, it's actually not even beyond our horizon. And are we lucky? Born in a particularly flat part of the universe. If the cause of the universe's expansion to explain the uniformity of the universe, but in fact, the universe is not so uniform. This will inform our understanding of the formation of the universe, and the theory of inflation have a significant impact. The second reason it's so controversial is he may not even exist. Kashlinsky's NASA team vs. Undercurrent believe, but the European Space Agency, ESA, Team Planck, using a more detailed map of the cosmic microwave background, they use themselves more data provided by the Advanced Planck detector. Ray examined the existence of undercurrents. The probe was launched in 2009. The Wilkinson Microwave Anisotropy Detector. 8 years after launch, after looking at 1,000 galaxy clusters, the Planck team claims to have seen no darkness at all, signs of flow, but Kashlinsky and his team. And we looked at the Planck data. They claim to have seen signs of an undercurrent. So there's still a lot of debate on this. Kashlinsky and his team announced in a paper they will use Planck and MOMAM data for deeper analysis to establish more conclusive evidence. But this has not been released yet until we find more evidence. Let's assume there's no undercurrent. There are no monsters outside the universe, billions of years ago, pulling thousands of circular galaxies towards him. It's a reasonable assumption. But like all unknowns, he does make humans think. Science doesn't really care about anything. The answer is the most convenient. Truth is truth, whether simple or complex. Maybe one day, we're going to find out somehow. To determine what lies beyond the visible universe, and whether the undercurrent is real, and we didn't solve a mystery. New mysteries will be discovered. The universe always holds new secrets waiting for us to explore. There's always more to know. Maybe it's the human hunger for knowledge and discovery. Never stop. It's time for the popularization of the civilian science brigade. Please also leave a message to discuss.